Hey, what's up, guys? This is Chung here. So this time, LeetCode 1895. Okay, so largest magic square. Uh, so you're given like a 2D board here, 2D grid here, and you need to find basically the largest magic square. So a magic square is a square, right? That's every row, the sum of every row and every column, and also the sum of both the diagonal and anti-diagonals are all the same, right? And the integers in the magic square do not have to be distinct, and obviously a cell itself, a 1 by 1 grid, which is one cell, is trivially a magic square, because this one obviously there's only one element. That's why it's a magic square by itself. Okay, and you just need to return the size. Basically, the larger the size, the size means the side length of the largest magic square that can be found within this grid, right? Yeah. So here's the example, right? I mean, the answer is 3 because uh, within this 3 by 3 square, right? Each row and each column, there will be the answer. The total sum is 12. So this is 12, 12, 12, right? And this is also 12, 12, and 12, and this same goes for the diagonal and anti-diagonal. So diagonal is also 12, and anti-diagonal is also 12, right? So that's why this one is the answer. Okay, and yeah, so that's it. I mean, there's some constraints like m and n, they're like 50, right? I mean, so for this one, I think there's no fancy solution here. So this one is pretty straightforward. Basically, we just need to check all the possible squares within this grid, and for each of the square, we check all the rows and all the columns, and plus those two diagonals, right? If they have the same sum, okay. And so, and basically there's a small improvement we can make here, so let's basically, given this kind of grid here, right? When we check uh the rows and columns, we don't have to check them 1 by 1, right? We can simply have like a prefix of each row and plus each column, so that we can just check this each row in all one time, right? And then we check each row, each column, and then plus these diagonals. And so that's it. I mean, nothing fancy. The only thing left here is just like the implementation, right? And then let's do it, right? So first, we need to create 2 presums, right, for each row and column. So we have this one grid, right, and it's going to be the length of grid 0. Okay, so that's, and then we have row presum. I call it row presum. I use the dictionary. You can also use the array. So I prefer dictionary because I can put -1 in it. So for I in range of n, right? So for each, basically this is going to be a dictionary of a dictionary, right? Because each element in this dictionary will be another presum for this row, right? So for each row, we define like this kind of prefix dictionary, right? So and then for j in range of n, right, we have presum of j is equal to the presum of j minus 1 plus the current value, right? And then in the end, we append. Oh, actually, so I'm sorry. This one is my mistake. So I mean, it's a list of dictionary. It's not a dictionary of dictionary. It's a list of dictionary. So the index here represents each row, and the value, the element in each of for each index is a presum dictionary. Okay, so that's why we have presum dot append this presum, right? Same thing for the columns, right? So for column presum, same thing. But this time, we need to loop through the J first, right? I think this one is M, yeah, and this one is this one is N, right? Because we're checking the columns one by one, right? Same thing, presum -1, 0, right? And then for I in range of M, okay, we have presum. I'll just copy and paste this one. This one is I, right? Because now we're checking the rows, the item on each row here. Same thing for I and J. So this is the row column, right? So that's it. That's how we pre-calculate the presum for each row and each column. Now let's just find all the squares, right? So the answer is 1 because that's the default, right? And then for I in range of M, and for J in range of N, right? So basically, we fix the up the top left corner, right? For example, if I is here, so we'll be finding, and we need to find basically all the possible squares, right? So how can we find that out? I do this. So for length, so the length in the range of 2 dot minimum of m minus I, and then the n minus j plus 1, right? So this is how I find find all the possible length of the side, right? For example, starting from here, we starting from 2 because we already taken care of the single cell case, right? So we just need to find all the possible length. So what's the maximum length we can possibly have, right? Basically, that's the minimum of these two value, right? And then we plus 1. Okay, and cool. And once we have that, we can so this is the basically I mean the current length of the current side length of the square, right? And since that we have a sum, right? We already have the sum. Basically, the sum will be the first row presum, right? It's going to be the ith row, and the last one is this one, right? So the column is this one. If we want to calculate the range sum, right? So the column will be j plus length minus 1, right? So that's the last column of the current square, right? And then we subtract the row presum of I and j minus 1. Okay, so that's the basically this is the presum, the first row sum, right? By using the presum, because I do it here so that I can have like a base case, right? Because I'll be using this sum as a base, and maybe we can do an early termination for the current for loop here. Okay, and then we're gonna have like diagonal plus nt diagonal, right, equals 0. That's the two diagonal value. And then I'm gonna have like a flag. So flag just represent, if this is a valid magic square. And then so now with the length, we know we have to loop through from 0 to this length, because let's say if the length is equal to 3 here, right? We need to loop through from 0 to 3 to check each rows, each columns plus these two diagonals, right? That's why for this I use L here in range of length, right? Yeah, so for we have a row, right? The row gonna be actually row is the same as this one. Similar as this one, but we need to add that, I plus L, right? Because we're moving the rows down. Okay. And if the row is not equal to the sum, right, then we simply do a flag equals to false, and then we break. We can do an early break here because we know this one is not gonna be the a valid magic square with the length equals to this, right? Same thing for the columns, right? I mean, I think I can just copy and paste this one. The only difference is that we're gonna have a column. So the column will be column presum, right? This one is gonna be j plus L, right? And then this one is I plus, right? So same thing for this one, j plus L, and then I minus 1, right? So it's basically it's in the reversed way. And then I can also copy and paste this one, column, right? Okay, and each time, right, since we're looping through this from 0 to 2, basically from this is a 0, 1, and 2, right? We can also calculate the diagonals, right? So for the diagonals, it's going to be the grade I plus L and then the J plus L, right? For the anti-diagonal, it's similar. It's going to be grade of still I plus L, but the column is in the reversed. Basically, the anti-diagonal is this, right? So it's going to be the J plus length minus L minus 1, right? So that's going to be the coordinates for the anti-diagonal, because we need to find this one, the top right corner, and then we going left, I mean southwest, right? Cool. So after this for loop, right, we maybe break, or if everything works fine for the rows and columns, we will also be having this kind of diagonals, right? That's why in the end we do a simple check. So if the flag is true, which means that we haven't broken because of the rows and columns, and the diagonals diagonal equals to anti-diagonal, right? Equals to sum, right? So if this everything are the same, then we know, okay, this is a valid magic square. We can just update the answer by using this L. I think this is going to be the length, right? Length, yeah, right. So this means that, okay, so a magic square with this length is valid, right? And then yeah, that's it, right? Then we just simply return the answer. Yeah, I think that's it, right? So run the code, accept it, submit. Cool, right? So at least it passed, right? I mean, nothing too fancy, right? So the time complexity, I think what I have here is this is a n, right? So we have a 1, 2, 3, and 4, maybe. Yeah, I think we have 4 nested for loops here. So I would say it's n to the power of 4. Yeah, this is somewhere here, because here we will loop through each square, and for each square we'll also be looping through the each row and column, right? Yeah. Mm, yeah, I think that's it, right? So nothing, nothing fancy for this problem. It's pretty straightforward. I mean, we just need to do a little bit of pre-calculations for the rows and columns, right? And then, yeah, simply just find, given like top left corner of coordinates, trying to find all the possible squares starting from here. And then for each of the square, we will be calculating the sum for each row and each column, and also and the diagonals as well. And then we just simply check if they're all the same, right? And then we update the answer in the end. Cool. I think that's it. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.